Let's take a closer look at standard reduction potentials, specifically tables of standard reduction potentials and the information that we can glean from them. The table you see here is really just a sample of a larger table of standard reduction potentials. Here's some things to note about this table. First of all, the table is organized so that the most favorable reductions, the most spontaneous, are on the top. You'd see that the most positive standard reduction potentials are on the top, the most negative on the bottom. So the most spontaneous reaction on this table would be the reduction of fluorine to fluoride. And I have it listed here as the most favorable reduction on this table. Now, as you go down the list, the reductions become less spontaneous, which means that the standard reduction potentials become less positive. All the listed reduction potentials here are actually determined from experiments where the standard reduction potential of the reduction of hydrogen ion to hydrogen gas is specifically defined as 0. So all the other reductions are relative to the reduction of hydrogen ion to hydrogen. So we will elaborate more on this in later slides, but for now we're just going to label this as our reference reduction, and remember that we've defined that as being 0 volts. Now when the reduction potentials turn negative, that means the reductions as written here become non-spontaneous and actually become more non-spontaneous as we go further down on the table and the reduction potentials become more negative. The most non-spontaneous or least favorable reduction would then of course be the one on the bottom, and this one is listed as a reduction of lithium ion to lithium metal. So we'll put a flashing sign here denoting that this is the least favorable reduction on the table. Well, let's continue to look at information we can get from this table. First of all, we can say that fluorine gas is the most powerful oxidizing agent listed on this table. That is, fluorine is extremely good at taking electrons away from other ions, molecules, or atoms because the reduction of fluorine to fluoride is so favorable by plus 2.87 volts, which is quite high on this table. In fact, on this table, it's the highest standard reduction potential. So F2, fluorine, the element, we would consider to be very electron hungry. It can strip electrons from many different reagents because the reduction of fluorine to fluoride is so favorable. So fluorine is the most powerful oxidizing agent, the most able to remove electrons from other reagents listed on the table. Now, as you go further down on the table, as long as the reduction potentials are positive, these other ions and molecules are also good oxidizing agents, but they become less so as you go down the table. So for example, permanganate is a very good oxidizing agent, although interestingly, it's a better oxidizing agent in acidic solution. You'll notice the reduction of permanganate at plus 1.51 volts occurs in acidic solution. There's hydrogen ions here. There's also a reduction of permanganate in basic solution. Notice the hydroxides here. That's still favorable by plus 0.59 volts, but not as favorable as in acidic solution. So we'd say permanganate ion is a better oxidizing agent in acidic solution. Now other species such as chlorine, dichromate, and not surprisingly, oxygen are also good oxidizing agents. And of course, anything listed here with a positive reduction potential could act as an oxidizing agent. Again, sometimes this depends on the pH and other conditions. So for example, oxygen can act as an oxidizing agent when it reacts with 4 hydrogen ions and 4 electrons to form water. There's also an alternate pathway where it can react with 2 hydrogen ions and 2 electrons to form hydrogen peroxide. That pathway not quite as favorable as the other. Now lithium metal is the most powerful reducing agent on the table, and I've got that labeled down here. This deserves some explanation. The reduction of lithium ion to lithium metal is very non-spontaneous, minus 3.05 volts. However, what this means is that the reverse reaction, that would mean lithium metal going to lithium ion plus an electron, is quite favorable, because remember, when you reverse the reaction, you change the sign of the standard potential. So we could write lithium metal going to lithium ion plus oxygen, which would be the oxidation of lithium metal to lithium ion, is very favorable. It has a plus 3.05 volt potential. Now what that means is that lithium metal is very anxious to get rid of an electron and form lithium ion. So we say lithium metal is a very powerful electron donor, a powerful reducing agent. Now other metals that are listed on this standard reduction table also are good reducing agents. So for example, sodium is a good reducing agent because if you reverse this reduction here, sodium metal going to sodium ion, that would be favorable by plus 2.71 volts. Aluminum metal is also a good reducing agent. Well, let's look at how we might use tables of standard reduction potentials to make some predictions. Consider the following list of molecules, ions, and atoms. What we have here is chlorine gas, chloride ion, silver +1 ion, and zinc metal. And what we'd like to be able to predict is which species, we call these, often call ions and molecules and atoms species, which species on this list would be the most powerful oxidizing agent? Well, in order to act as an oxidizing agent, a molecule, ion, or atom must be able to accept an electron or electrons, and those most favorably disposed to do so would have the most positive standard reduction potentials. They would be the best oxidizing agents. So what we're looking at is which one of these would be the best electron acceptor on the list, because that would be the most powerful oxidizing agent, the most able to remove electrons from other reagents. Well, what we're going to do is write out expressions for the reduction of each of these and evaluate which would make the best electron acceptors or oxidizing agents. So I write out the reduction of chlorine to chloride, and if you refer to the table on the previous slide, the standard reduction potential for this, you could read right off the table, is plus 1.36 volts. Let's look at chloride. Well, how easy is it to reduce chloride? Actually, it would be very difficult, because you'd be forming chloride, not a chloride ion, you'd be forming a Cl2- ion. And actually that's not quite possible because a 2- Cl ion does not exist as a stable ion. If you recall from General Chemistry 1, a chloride ion is fairly stable because it has an octet of valence electrons. So adding an extra electron beyond that octet would be an unstable situation. The other clue that you might have that this is not a great reaction to write is that you can't find this on that table of standard reduction potentials. How about silver ion being reduced to silver metal? Well, sure, we can find that on the table. It has a standard reduction potential of plus 0.8 volts. Finally, how about zinc metal picking up an electron to form a zinc minus ion? Well, we're going to cross that one off the list. Remember, metals typically form positive ions. They're good at losing electrons. So that leaves us with the reduction of chlorine, Cl2, and the reduction of silver plus ion. So both of these can act as oxidizing agents because both chlorine and silver plus ion are capable of accepting electrons from other reagents. But the best oxidizing agent would be chlorine because it has the highest reduction potential. When we write it as a reduction to chloride, it has a higher standard potential than writing the reduction of silver ion to silver metal. So chlorine is the most powerful oxidizing agent on the list. How about if we wanted to know which one of these would be the best reducing agent? Well, in order to act as a reducing agent, a molecule, ion, or atom must be very good at donating or giving away electrons. And those most favorably disposed to do so would have the most positive standard potential for oxidation. Those would be the best reducing agents. So what we're going to do is write out expressions for the oxidation of each one of these on our list and see which one would be the best at being oxidized, or would have the most favorable oxidation. Well, oxidizing chlorine to Cl plus ions, we're going to cross off the list right away because Cl plus does not exist as a stable ion. And again, you wouldn't find it on that list of standard reduction potentials. You wouldn't find Cl plus electrons going to chlorine. How about chloride being oxidized to chlorine plus 2 electrons? Well, we can find that on the table of standard reduction potentials just written backwards as an oxidation. So its standard potential is the opposite sign of the reduction. So the standard potential would be minus 1.36 volts, not a very favorable reaction. How about silver ion going to silver 2 plus an electron? Well, we're going to rule that one out because silver 2 plus is not a very stable ion for silver. If you're not comfortable with that, we can just leave it that you're not going to find this on a table of standard reduction potentials. You're not going to find the reduction of silver 2 plus to silver plus ion. How about zinc metal going to zinc 2 plus 2 electrons? Well, sure, you're going to find this on the table of standard reduction potentials written as a reduction. You're going to find it as zinc 2 plus 2 electrons going to zinc. And the standard reduction potential for that, the potential of that would be plus 0.76 volts, which is the opposite sign of the reduction listed on the standard reduction potential table. So if we look at this, we'd say only the oxidation of zinc metal has a favorable or positive standard potential. So chloride can be oxidized to chlorine, but it's unfavorable. So under certain conditions, sure, you could make chloride be oxidized to chlorine, but only zinc seems to be the only one on the list that is anxious to give away electrons. Its oxidation potential is plus 0.76 volts. Let's do another example here. Using the same table of standard reduction potentials, which again, I'm not putting on this slide for lack of room, which is a little annoying, but I will bring the potentials out from the table when we need them. So a question that would be fair to ask, a type of question that would be fair to ask would be, would you expect a spontaneous redox reaction between dichromate ion, Cr2O7 2-, dissolved in water, and iron 2+ ion dissolved in water, where there's also hydrogen ions, in other words, in acidic solution? Well, let's take a look at this. On the table of standard reduction potentials, what you want to do is find and write out the reduction half reactions and their associated potentials for any reactions involving these two ions, no matter whether the relevant ion appears on the reactant or product side of the reductions. So for dichromate ion, if you look on that table, the only reaction listing dichromate would be the reduction of dichromate by 6 electrons with 14 hydrogen ions involved to chromium 3+ ions in water, and it's quite favorable by plus 1.33 volts. Now for iron 2+, we actually find two half reactions on the table that involve iron 2+. One is the reduction of iron 3+ by 1 electron to form iron 2+. The potential for that is listed as a favorable plus 0.77 volts. It also lists the reduction of iron 2+ by 2 electrons to iron, metal. That's listed as an unfavorable reduction, minus 0.44 volts. Well, it appears that dichromate can only act as an oxidizing agent, accepting electrons, and it's a very good one because it has a very positive reduction potential. So we need to ask whether or not it's powerful enough of an oxidant to oxidize iron 2+ to a higher oxidation state like iron 3+. So only one of the two reduction half reactions from the table involves both iron 2+ and iron 3+, and that would be the top one listed here. So I'm going to write down here iron 3+ plus an electron going to iron 2+. That's our reaction from the table that involves iron 2+ and iron 3+. We're going to reverse that and write it as an oxidation half reaction, iron 2+ to iron 3+ plus an electron, so the potential changes sign. And so if dichromate is reduced and acts as an oxidizing agent, and iron 2+ is oxidized to iron 3+, the overall potential for the reaction would be the voltage or the standard potential of the reduction of dichromate, that would be plus 1.33 volts, and the oxidation potential of iron 2+ going to iron 3+, which is unfavorable by 0.77 volts. So you'd add plus 1.33 minus 0.77, but it would give us a positive overall potential of plus 0.56 volts. Therefore, we would expect dichromate to spontaneously oxidize or remove electrons from iron 2 in acidic solution. The dichromate half reaction does require hydrogen ions, thus our conclusion is only valid in acidic solution, specifically 1 molar hydrogen ion concentration, since we're working under standard conditions. Now, if I haven't lost you totally by now, and hopefully I have not, one question you may have is, hey, shouldn't we balance the redox reaction? The redox reaction, of course, is the reaction of dichromate with iron 2+, where the dichromate takes electrons and is reduced to chromium 3+, and iron 2+ gives the electrons and is oxidized to iron 3+. But this whole thing seems out of balance. The dichromate is picking up 6 electrons each, where each iron 2+ only gives up 1 electron to form iron 3+. So again, you might ask, shouldn't we balance the redox reaction before we make this conclusion that the entire reaction is favorable by plus 0.56 volts? In other words, we just added 1.33 volts to minus 0.77 volts and completely ignored the fact that our equation, our redox reaction, wasn't balanced. The number of electrons gained here doesn't seem to be equal to the number lost here. Well, potentials, E0 values, are intrinsic properties of reactions. Now, what that means is that the potential, the E0 values of each half reaction, would remain the same and would add together to give the same overall potential whether or not each half reaction was balanced against the other with respect to charge and mass. Another way of saying that is, let's suppose we did balance it, and let's take a wild guess that we would need 6 iron 2+ to balance it, because that would give 6 iron 2+ going to 6 iron 3+ plus 6 electrons, which would perfectly balance the 6 electrons being gained by the dichromate. So we'd write 6, we'd put a 6 in front of the iron 2+, a 6 in front of the iron 3+, and make this 6 electrons. Would we multiply this E0 value by 6? The answer is no, don't do that, because the potential for iron 2+ to go to iron 3+ is unfavorable by 0.77 volts, whether there's 1 of these or 6 of them or 1,000,000 of them. Potential is an intrinsic property. It doesn't depend on the amount of substance present. So we were safe by just adding these two potentials together.